guys, welcome to our first online lesson. So remember, one of the advantages is going to be that these are videos, so you can go back, look at it again. And another very important thing, and do this as much as you can, is to, whenever we do a problem, pause the video, try to solve the problem for yourself, and then look at the solution. Okay, that's a way to learn. You're going to have to take more responsibility now for your own learning process. That's a bit different now. I cannot monitor how you learn as much as I would do if I'm with you in classroom. So it's now your responsibility. Okay, so we go to sequences. I'm going to do a little bit less than what the textbook does because I'm going to focus on the things that we really need to do. Okay, so what is a sequence? A sequence here, I have written already two sequences for you. One, what you notice is it's a bunch of numbers, a sequence, right? But you see the dot, dot, dot here. The dot, dot, dot means, well, it doesn't stop. There are more numbers to come. And in fact, how many? Infinitely many. That's what a sequence for us will be infinitely many numbers. What does the dot, dot, dot mean? Well, in cases like, let's look at the first sequence, it's a bit like this IQ test, right? You can try to figure out what's the next one, and what's the next one, and what's the next one. In other words, recognize the pattern. Now, we're not going to concentrate on that at all, so I'm just going to discuss with you what the pattern is right away. We're not going to focus on solving a Q test. That's not what we want to do, okay? So, but in order to talk about these things, sequences we're going to denote by subscripts. So this n here, so n will be an index 1, 2, 3, 4, and of course, again, there have to be infinitely many. And we start numbering like this. A1 would be 1 then, and A2 would be 2, A3 would be 1 over 3, A4 would be 1/4, etc. Okay? So, as I said, what we really need to know is what is an. So if we let n be some arbitrary index, we need to know the formula for that. Now, I guess everybody sees that this is 1 over n here. Okay? And conversely, if you have a formula like this, you can now find what the elements in this sequence are. You simply put in values for n. N equals 1, n equals 1, n equals 2, n equals 3, n equals 4, and so on. So let's do this, for instance. Let's suppose that I have the following formula: 3 plus n divided by 4 plus n. Let's write down what the first few numbers are. So if n is 1, then a1 is 3 plus 1 over 4 plus 1, that is 4/5. If n is 2, then a2 is 3 plus 2, so the value for n is 2. 4 plus this becomes now 2, so this is 5/6, and so on. Okay, so that's how we'll talk about sequences. Sometimes, as you say, you see the pattern, but even if you see the pattern, everybody can guess that the next element is, let's see, next element is going to be 5 over 6 here, right? And then next is 6 over 7. But how you write this down can be sometimes a bit tricky. So that's why I'm saying I'm not going to focus on that, and I'm just going to say an in this case is just n over n plus 1. But now we have to be a little bit careful. I said we let n be from 1, 2, 3, 4, but you can also take n to be 0, 1, 2, 3, and so on. You can start, in other words, at 0 instead of starting at 1. And it makes sometimes it's easier to do with 0, and sometimes it's easier to start with 1. In the first case, it was very easy to start with 1 here, because then we had this very nice formula, an is 1 over n. But you see here that is different, right? If I put n equals 0, I get 0 over 1. That is exactly the first element here. So a0. The zeroth element, it sounds weird, right? So I'm just going to say it's the first element, but okay. And this then, if you plug in n1, you get 1 over 1 plus 1, that's 1/2, so this is a1, and this is a2, and now you can check that everything is as I said it was. So this is something you have to get used to. It depends what we want to do, whether we start from n equals 0, n equals 1. And of course, once we make choices like that, we can actually decide to start wherever we want. But most of the time it will be 1 or 0, depending on the situation. I didn't say it here in this example, I didn't say where we start, but we could have taken n equals 0 here, right? And then we would have a0 would have been 3/4. It's just whatever we want to do, we have to actually, whenever you talk about the sequence, we should say what the values of n for the sequence are. Okay, that's enough about these sequences, but I want to now draw the attention to one very special sequence that we're going to need quite a lot later on. And it's a very simple one. I'll write it up for you. It's 1, minus 1, 1, minus 1, 1, minus 1. And now you can guess what the next one is, right? So 1 and so on. So it just alternates, that's the term Redpan uses for that, alternating sequence. It alternates the signs, plus and minuses, in a very regular pattern. Now, if you could start think about, you can try to guess what the formula is, but if you have not seen the formula, it's not so obvious to guess it. Once you've seen the formula, it's so obvious. It's so obvious that you're never going to forget it anymore. Well, that's at least I hope. So what's the formula? I'm just going to give you. Here, as I said, we have to make a convention that we start with 0, 1. I'm going to start with 0 here, for a reason that you will see very shortly. And with this, so starting from n equals 0, 1, 2, and so on, the series is given by the following formula. And what we're going to use is the simple fact that the powers of minus 1 has only two different powers. If it's an even power, you get 1, and if it's an odd power, you get negative 1. And that's exactly what we want. So minus 1 to the power n. Whenever n is even, then the result is n is is 1, right? And whenever n is odd, then n is negative 1. And that's exactly what happens here, right? So remember this formula, that's going to be very useful later on when we need this, when we talk about sequences and series later. Okay, so these are the series. There's another series that we will talk about in a while, but I want to already tell you about it. It's the so-called geometric sequence. But we'll come back to this, so don't stress too much about it yet. And the example, I'll give you an example right away so that you don't, that we can discuss it. So the geometric series that I'm thinking of here is, an example is this one here. Okay. And okay, again, I think, well, pause the video and think about it. What do you think is the next element? And when you answer this question, think about two things. Is it going to be positive or negative? And, well, I'll tell you what the numerator is, right? That's going to be 2. So I'll do this in green. The next element is definitely going to be a 2 in the numerator. It seems that we have plus, minus, plus, minus, plus. So this one should be a minus. So there's going to be something in the same, we're going to use this trick to get the minus coming there. And what's the denominator now? Well, let's look at the denominators here. The denominator, right? 3, 9, 27, 81, powers of 3. Now, this is also even true here because that's actually 3 to the power 0. Now, what does actually this mean? This means that if I look at let's look at the first number. How do I get from there to there? That is by multiplying. Let's figure out what I multiply by. To get from 2 to minus 2/3, well, I multiply with minus 1/3, right? If I do that, then I get this element. But notice that this actually same thing happens here. Multiply minus 2/3. Multiply this bit, this minus 1/3, and I get minus minus is 2, in the bottom 9ths. And now you can check that each time the same thing happens. And that is what a geometric sequence is. A geometric sequence is a sequence in which the next number is obtained from the previous number by multiplying with a fixed factor. And this factor we will call R, the ratio. This is the ratio of the geometric sequence. I'm just saying this now so that later on when we talk about it in more detail, you have already seen it. Okay, I don't think there's a homework problem in it. So let's go on to what we really need to talk about now. A very important concept for us is going to be, and a concept that we have seen already in Calc 1, is the limit of a sequence. This is something we're going to have to do throughout this chapter, calculating limit of a sequence. And the limit of a sequence is really the same as what the limit of a function is. So if, let's go back to our sequence that we had here, the first sequence here, what we kind of asking is what is happening at the end of the sequence. Of course, that's not really correct. That doesn't exist really, it's an infinite, but limits allow you to say this. So what we want to know is if you have so En is a sequence given by some formula. Not every sequence is given by a formula, but we won't deal with things like that. We always will have a formula. So we have En as a sequence, and what we want to calculate is the limit of this sequence. Now, what limit do we talk about? Well, there's only one thing, right, that we can talk about is how does it go to infinity? When this index n goes to infinity, what happens to the value of a? And remember, a limit means that if you would make a table and you take bigger and bigger n's, then you get a value that is closer and closer to the limit value. Let's do this on the sequence we had. Remember, our first sequence here, I'll scroll back for you to show, was given by the formula 1 over n. So an is 1 over n. Okay, so in this case, the limit is the limit for n going to infinity of 1 over n. Now, the same trick, the same techniques that we use for limits of functions applies to limits of sequences. There are some extra things that we have to be worried about. I'll tell you later, but for now, it's what we try to do is you try to plug in infinity, 1 over infinity. Does this make sense? And in this case, we know this is a definite form. We know what 1 over infinity is. 1 divided by a very big number is a very small number. So in the limit, we get 0. So the answer is, this is 0. Okay. Let's look at the other sequence. We had the second sequence that we had here was this one. Right? The sequence, that's this sequence here. What's the limit there? You can see that it's perhaps a little bit harder to guess here, right? So let's try to figure out. So what's the limit for n going to infinity of the formula was 3 plus n over 4 plus n. 3 plus n. No, that was not the formula. Sorry, I'm pointing to the wrong one. No, sorry, this was the formula here. This is the formula. Sorry, I was pointing to, this was the formula for this sequence. N over n plus 1. N over n plus 1. Okay, as always, try to plug in infinity. You get infinity over, well, n plus infinity plus 1 is also infinity. Now remember, this is an indeterminate form. We have talked about this now already. Indeterminate form. And there's several techniques we can do. One, of course, is L'Hopital. But it's sometimes there are better techniques for functions that are simpler like this. Do you remember it? If you don't remember, okay, I'll explain it, but you try to figure it out yourself. It is dividing by the highest degree term. Divide by the highest degree term. So in this case, of course, that would be just n. That's all. It is both top and bottom have the degree n. So what does this mean? So let's work out I'll copy it again. we have n over n plus 1. We're going to divide both top and bottom by n. So we divide by n, divide by n. Now, dividing by top and bottom by n means every single term. Okay? Be careful to not just scratch out the front ends here, but also don't forget this one. Okay, so let's work out what we have now. This is the limit for n going to infinity. The top has become 1, the bottom has become 1 plus 1 over n. The n is still there. We cannot always hope to get rid of it, but what happens now is if we try again, that means we plug in infinity, get 1 over 1 plus 1 over infinity, and remember, 1 over infinity is 0. So this is now 1 over 1 plus 0, which is just 1. And that's how we calculate limit of what we call rational functions, fractions of polynomials over another polynomial. That's the technique, dividing by the highest degree term. Okay, let's practice this. So I'm going to do this problem, but you should try it before we actually work it out, before you look at the solution. 3n squared plus 4n plus 1 over 5n cubed plus 6n plus 2. Okay, so we divide by, here, what is the highest degree term? So highest degree here is, be careful, it's either, we have to look, here is a 2, but here's the 3. So the highest degree is n cubed. That's what we have to divide by. So this would be, so we have to divide by n cubed, n cubed, n cubed, n cubed, n cubed, n cubed. When you do this kind of calculations, do not skip a step. It's when you skip steps, people start making mistakes left and right. So just do it the way I do, step by step, divide everything by n cubed, then work out what you get, namely simplify. So that's the limit for n going to infinity. Simplify. If you divide n squared by n cubed, there's an n left in the denominator, which we just keep like that. Here, this one simplifies to 4 over n squared, and the last one is just 1 over n cubed. And in the bottom we get the n cubes cancel in the first term, 5. In the second term we have a 6, 1 over n, 6 over 1 squared, right? Well, we can put the 6 on top. Let me put the 6 on top. There's no need to not do this. And then plus 2 over n cubed. Why do we do this? Because 1 over infinity is 0. So whenever we plug in infinity here, so we're going to plug in infinity, let's show here, we're going to plug this, if we put this equal to infinity, we're going to get 3 over infinity, which is 0. Okay, so this would be 0 plus this term, same thing, and this same thing, because cube of infinity is still infinity, right? Now in the bottom we do get the 5 here. This though is 0, and again this is 0. Okay, so all they go to 0. Sometimes we denote this like this, by little arrow saying it goes to 0. So what's left is 0 on top, 5 in the bottom, that is just 0. Okay? Alright, so that's how you calculate a limit of a sequence when it's given by a formula like that. But that's not the only way, that the technique that we have to solve this kind of problem. So here's I'll do another one of this one first. So let's do one involving radicals. You might think, oh, this is going to be hard, but it's actually not so hard. So a limit for n going infinity of, let's do radical n plus 4 divided by radical n plus 1. Well, there's a couple of things we can do now. We have to be careful with the radical. We cannot distribute the radical. But what we can do is take the radical of the whole thing. Bring the fraction inside the radical. Because the rule is that if you take a radical of a fraction, then it's the same. If you take a radical of a fraction, it's the same as the radical of the numerator divided by the radical of the denominator. Okay, that is one of the rules of radicals. And then I can use a fact that we have also used a lot when we come to limits, is that you can actually bring a limit inside a function. So I can actually say, well, it's the same as the radical of the limit of n going to infinity, n plus 4 over n plus 1. And then this limit is now again of the form is of this form here, rational function. So we do the same thing as we did last time. I forgot. No, not right. So the radical of the limit for n going to infinity, and I'm going to divide now everything by n. That's the highest degree here, right? N, 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 and n. So we get 1. This cancels out. The next term is 4 over n divided by 1 plus 1 over n, and then we use that these two go to 0. I have now explained this, I hope enough. Right? So we get the radical of 1 over 1, which is of course radical of 1, which is just 1. Okay? So remember, so the trick here that we used is that we can, this here at this point here, that we can bring the limit inside. Technically, this only works for functions that are continuous, but that means every single function that we ever run into are continuous. So we shouldn't worry about whether this holds or not. Okay. Other rules of limits that we know is, let me just show an example. Suppose you have to calculate the limit for n going to infinity of 1 over n plus 3n. Okay, you could put this on a common denominator, but it's going to be a lot of work. We know very much that we can split the limits. We can say it's the limit for n going to infinity of 1 over n plus the limit for n going to infinity over 3n. We can distribute the limit over product. And the good news is you can go through everything. Products you can do as well, whatever you want. So here we go for the sum. Okay, the limit of 1 over n, that's 1 over infinity, that is just 0. Plus, what is the limit this one? Well, 3 times infinity, that is just infinity. Now, so that's 0 plus infinity. That is nothing special. If you add nothing to infinity, you still have infinity, right? So that's the answer here. Add some terminology, perhaps. That's something, again, shouldn't worry too much about yet, but later on we'll talk about it. When our outcome is infinity, or sometimes even the limit might not exist. I'm not going to give you an example of that. But if you get infinity, we say that the limit is divergent. We have seen this before, right? When we had improper integrals, there was also limits. And if the limit was infinity, we say divergent. And when the limit is not infinity, so when it really is a number, then we have convergent. Okay, so that's some terminology that might be used. All right, so as I said, there is much more that one can do here, and you'll see that the textbook has many more problems to work with, but I don't want to discuss them now, because what we will do is not really study sequences. We will study something which we'll call series. We'll do that on the next lecture. Okay, so let's do one more problem. Oh yes, there's definitely one more problem that we have to do. So far the technique of finding limits was using dividing by the highest degree term, but that is not always possible, right? And there is actually, so let me just explain here. So let's look at the sequence. AN is a sequence EN divided by N. For simplicity, I take it rather simple. Now let's see what happens if we want to calculate the limit. Okay, so this is the limit of En over N. If I plug in infinity, we get e to the infinity, which is of course just infinity, and n to the infinity is also infinity. We get infinity over infinity again. So in indeterminate form, I'll remind you of this, indeterminate form, which means we have to do something more. This is never, never, ever the end of the story. Please make that's very important. That doesn't mean divergent, doesn't mean convergent, doesn't mean nothing. It means we still have to go on. Okay, what do we do? Well, there's no highest degree term here. This is an exponential function. So we have seen when we talked improper integrals about a very strong properties. Way of solving this is called L'Hopital's rule. I write it this way. You might have learned it a little bit differently. Remember, this guy named L'Hopital means hospital. So whatever you call it. And it is luckily a fraction. So L'Hopital's rule applies to it. And remember what it means is that if f of x divided by g of x is infinity over infinity, or 0 over 0, that's also, so this is if the limit for x going to infinity is either this or this, then we can also calculate this limit by using the derivatives of both of these functions. So that was a little bit sloppy here. Okay, but that's not a chain rule. Okay, I already pointed this out. What's the difference is, well, f and g are functions here, where an is a sequence, but it is clear that this sequence is actually given by a formula that is actually a function. The function that we have here is the function e to the x over x. Okay, and so that if f of n is exactly an. So we say this sequence is mimicked or is given by an actual function. Be careful, that's not always the case. And I'll give you some examples where it's not the case, and so that we cannot use this technique. But if we are in this case, we can use the L'Hopital's rule. So let's go now what we need to do. Okay, so this limit, and I do this to make sure that everything is really correct, but some people sometimes skip this. So I'm replacing this limit, which is a limit of a sequence, by a limit of a function. The function that mimics, that gives me the sequence. And now really in the satisfaction of L'Hopital's rule, right? If I plug infinity, I get infinity over infinity, and so I can now use L'Hopital. So here I use the L'Hopital's rule. And that says that's the same as the limit for x going to infinity of the derivative of ex is ex, and the derivative of x is 1. And if I plug in infinity now, I get e to the infinity, which is of course just infinity. So this was actually a divergent sequence. But that's something we could not predict from the indeterminate form. You'll see there are examples where it's just the opposite or something else. Anything could happen here. Okay, so let's do another thing, of course, what you need to know is sometimes the behavior of functions at infinity. If, for instance, we here use that ex at infinity is ex. So, for instance, if the sequence is an is e to the minus n, then we see that the limit of this sequence, e to the minus n, is e to the minus infinity. That's actually really e over infinity, so that's 1 over infinity, which is 0. Okay, this is because this function, the function e minus x, is exponential decay. Another example where you have to see what happens is, let's look at this sequence, 1 over n. An is ln of 1 over n. ln of 1 over n, sorry. So let's take the limit of the sequence. Ln of 1 over n. Again, we can bring the limit inside. That was one of the rules that we explained before. So it's the ln of the limit of n going to infinity of 1 over n. Now this is very simple. That is, limit of 1 over n is just 0. Right? 1 over infinity is 0. Now the ln of 0, remember the ln looks like something like this. And we actually have a vertical asymptote at 0. So this means that the ln is actually negative infinity. Therefore, this series was actually divergent. Okay. As I said, there are some sequences that cannot be given by formulas and by functions. And let's go back to one of these very early ones that I discussed here. Let's look at this one here. The alternating sequence. We had a formula for it, but notice that this cannot be a function. The function, let me erase a little bit here, make a bit space. We don't have a function. Minus 1 to the power x does not exist as a function. You might say, why not? I can plug in x, why not? Well, try to plug in a half. What do? A power a half means we're a radical, so you have to take the radical of -1. Yeah, good luck. That's a complex number, and that's what we don't deal with that, right? Remember? So as a function, it doesn't exist, so we cannot use anything else like the L'Hopital rule and so on. So we could ask, what's the limit here? But think about this. 1 minus 1, 1 minus 1, 1 minus 1. What does the limit mean? It means you get closer and closer to this number. Well, you're never getting closer and closer to anything, because you might at some point be close to 1, well, actually equal to 1, but the next you're actually -1, which is too far away, and it never gets better. So this is an example where the limit of this sequence -1 to the n does not exist. It's not infinity, it's nothing. And of course that also will count as divergent for us. So there's another example of what we call divergent. Now you might say, oh, okay, I understand. Whenever you have this alternating sequence, the alternating sequence is going to be like that. No, that's not the case. So here is an example where the limit does exist. Let's look at the limit for n going to infinity of -1 to the n. This is going to make it alternating divided by n. Okay? So if I would plug it in, it gets a bit tricky now. How do I going to plug this in, right? What is -1 to the infinity? Does it exist? Now the bottom is infinity. Okay, so in this particular one, I'm going to reason rather than use an extra method. There is a method here, which the book explains, called the squeeze method. But for us, we're going to just think like this. We say, okay, let's look at what 1 over n is. The limit for 1 over n is 0, because it's 1 over infinity, right? So I plug in infinity, and 1 over infinity is 0. Right, so that we know. What's the difference is that we have a negative sign here. So what's the difference between these elements and these elements? Right, let's write them up. Obviously, we cannot start from n equals 0 here, because then we're in problem, right? So in this sequence, the first element would be -1 over 1. The second one would be -1 over 2. Sorry. Now we have an even power, so it would be actually plus. Then we got -1/3. N is 3, so an odd power. 3 here. The next n is 4, we get an even power, so we get plus 4, etc. In this sequence, we do the same thing, but now we don't have signs. So it's 1 over 1, 1 over 2, 1 over 3, 1 over 4. They're different, at least the odd labeled ones. But if you notice, this one we know goes to 0. This is what it means that the limit is 0. Now this one also, in magnitude, the numbers go to 0. Though they do alternate, they get positive magnitudes, but they still all get closer and closer to 0. So this also goes to 0. It's in a different pattern. This goes like this. This is the function 1 over x. Here we get something different. We get actually something, let me sketch you what it is. If you don't understand it, don't worry too much about it. If you would plot these points, you would get something here, -1. -1 is here, and the next one would be there, the next one would be there, the next one would be there, this one would be there. So this here is supposedly 1/4. Okay. So this is my A4. Sorry. A half. This is A2. This is -1, so this was A1, and this would be A3, and so on and so on. And you see they lie on two different curves, but these two curves both have a horizontal asymptote, and they both therefore go to 0. Okay, and so that's why we say that this limit is 0. That's a special case that we sometimes will run into. Okay, I think we did everything that we needed to do, and so we have some homework problems that I want you to do. Now, I don't want you to do all the homework problems, so I will list in the comment the problems that I want you to do. But remember, there's always going to be, apart from doing all the problems that are given on the syllabus or that I give you, there are always two problems I want you to do more in detail and show me by taking a picture of your work that you actually worked on them. I don't want you to take a picture of everything because that might be just too much, too long. And so you have to take a picture of this thing and email it to me. That as explained already on the website. And so the two homework problems, so the special homework problems, let me call them that, are number 27. This is all from 5.1, right? 27, so 5.1, 27, and number 46. But I'll put this in the comments. So don't forget that once you have viewed this entire movie, and you have to be honest, and only when you have viewed the entire movie, put a comment with your name but in underneath this movie. Don't forget the comment. Sometimes depends on what app you use, might be all the way in the bottom. So you have to put a comment. You have to subscribe. I repeat this. You can, if you want, put the notification that tells you when new YouTube movies of this course will appear, so that you can look at them already at whenever you want. But don't forget to put the comment there. And if you have questions, you can also put them in the comments, or you can email me. Either way will work. I will check both. All right? Okay, that's enough for today. I'm gonna also, from probably next week on, we're gonna start with our quizzes, and we have to make up some of the stuff we have not done yet. That was supposed to be our test. But all that will be explained on the webpage. Bye.